Got it. We are recording. We're live. RAI workshop number 2. And Danilo. How are we all doing today? Hi, Barnaby. Sam Taggett. Danilo, welcome.
Hi, everyone.
And Davide. All right. A few more joining. And we're just dropping the link one more time in the Discord channel. See if we can drag anyone else in. Awesome. Thanks, Patty.
Yeah, let's see. Wait for people to join us.
Yep.
Hello, everyone.
Oh, yeah. I don't know if Patty was able to introduce herself last
No,
time.
I will do it now in the Discord channel. Yeah.
But yeah, exactly. You got to send your intro. And you can do a quick hi right now too if you want.
Yes. Hi, everyone. I just joined the T Academy, and I have a background in board games. I've worked for 6 years playing many games and producing them. But now I'm in the crypto sphere, and we'll help with yay. And we'll help you with what I can. And I hope that I learned something with these RAI workshops.
Yeah, Patty's an all-star. Welcome, Patty.
Yay. Not sure about the all-star, but yeah.
All right. Yeah, so I think with 5 minutes past, we could get started. Danilo, I actually don't have any intro slides and wanted to make sure that we had as much time as we could to go over the interesting stuff. So I'll just hand it over to you right away, actually, to get started.
Yeah, sure. So I think that we can start. I'll share my screen here. Are you guys seeing?
Yep, all set.
So yeah,
all good, thanks.
So yeah, workshop 2 of the RAI Digital Twins. And I mean, going back to the outline, on the first workshop, we did have an introduction to RAI and also digital twins in general. So we did have the introduction about how RAI works and so on. We also had a section about what are digital twins, what's a design digital twin, what's operational digital twin, and what's the overall RAI digital twin architecture in terms of those two. And we did have a hands-on section where we actually, let's say, executed the RAI digital twin and discovered how to run it. And we also had some challenges. We had several submissions, and it was super cool because, I mean, for a lot of the people that did submit over this week, it was actually their first pull request at GitHub. So yeah, happy to, let's say, to form new open source contributors. And yeah, on this workshop, it's going to be more about, let's say, understanding how the RAI digital twin workflow works. So we are going to have a deep dive on the input and output, and also about how the execution cycle works. And next workshop, we'll have also a deep dive into the actual cadCAD model and also how you could, for example, include behavioral models and so on. So yeah, I think that you guys all already know from the first workshop, but anyway, we do have some challenges for each workshop. And I mean, it's fully optional. You can do as much you would like from them. And our submissions are going to be accepted. So, I mean, even if you hadn't submitted for the first one, it's also an opportunity. I mean, you still can, let's say, do submissions for the first one, no problem. And yeah, going over quickly how this workshop is going to be. So, I mean, we have this intro piece. We are going to have a walkthrough on the input and output. I'm going to, I mean, talk about, let's say, I'll not give spoilers for now. After that, we have a 5-minute break. So I mean, you guys can go get a coffee or maybe ask some questions. And after that, we go on the execution cycle of the digital twins. So we are going deep into the code about how the execution works. And then I'm going to talk a bit about the challenges that we have for this workshop. And then another big time where we can have questions and answers and discussions. So yeah, starting the first section about the input and output. So it's going to be more hands-on because I'm going to open my VS Code and we are going to walk through it and so on. But I think it's useful to provide a summary first about what are the inputs and also about what are the outputs. And in regards to the inputs, I've mapped here essentially all, let's say, all the pieces that you could modify so that, let's say, you could have different simulations without, let's say, tweaking too much on the code. So the idea here is that we really have, let's say, 6 places where one could modify so that, I mean, they could tune a parameter or see how things would behave in a different scenario. How someone essentially would, I mean, tweak any input so that, yeah, everything that, let's say, is sort of a free parameter on the simulation. So as you can see here, there are specific, so there are the execution cycle parameters. They are related to the actually to the simulation configuration parameters, which is things like, for example, for how much time do we want to extrapolate to the future, or for how much historical data do we want? Do we want to use 1-2 days of historical data, 1-2 weeks of historical data, 1-2 months? So those are all parameters. You can define both by the command line interface as we saw on the first workshop, or there is also this main file here where you have some default arguments. We are going to go over them. Another option for inputs are the historical data. So the idea here is that one of the pieces of the digital twin is about retrieving data. And we really have 2 options. We can retrieve that data as we run it, or we can use the last data file. So suppose that, let's say, you want to do a simulation with by using, let's say, fictitious historical data for, let's say, maybe you, for example, are motivated by having counterfactuals. It's possible to generate, let's say, a file that contains, let's say, scenario for this alternate history, and I mean, make the digital twin run it with it. You are not obliged to, let's say, download out the data. So this is another source of input. There is also about another input, which is governance events, because the controller parameters of the high, like, for example, the P part, because as you guys know, high has a high PAD controller for the redemption rate. And, well, the P and E terms, they are controlled, I mean, they have parameters for that, and we have this file controller params here on the data folder that, I mean, have values for them over the time. And also, I mean, probably most of you guys, I mean, already know cadCAD at least on a glance. And as you guys know, cadCAD has an initial state that needs to be used, and also some simulation parameters. And they are on those paths here. And the last source of input that you could use for controlling the execution is really the notebook templates. And we are going to go over a bit how it works. So those are the 6 inputs. And we also have those 3 outputs here for the digital twin. So everything that the digital twin does is really, let's say, to generate those things. First one is really metadata. No big surprises there. I mean, it's just things like, for example, when it was executed. And it's what the metadata on the data sets that are on this data folder. About data sets, I would say that this is the core output of the digital twin. So for example, we have this ham data here, which is essentially the HL part of the digital twin. I mean, you go to the graph, you download data for the arguments that you have provided on the input, and you are going to have this ham data here that was not processed. And by using that data, the digital twin, I mean, performs backtesting, and we are going to go, I mean, we are going to go over a bit on the next section. And also we perform extrapolation. So backtesting is really, let's say, the data on the past, but with 2 variables. One, which is the actual data. The second one is what our cadCAD model thought it should be. And the extrapolation is really, let's say, predictions over the future. And the third kind of output is the report. So as we are going to see, we have notebook templates. And the idea is that it's one of the inputs. And as we go over the execution cycle, we essentially generate those HTML files. So that's the summary of it. And I think it may be useful now to go over, let's say, each one of those just to see how it is. So for example, let's start with the execution cycle parameters here. If we go to the VS Code, as I said, it's contained inside RAI Digital Twin main. And those parameters are really things like, for example, the number of past days to load, number of extrapolation time steps, and whatever to use the last data or not. And the thing is that those parameters are going to be fed into this function here called extrapolation cycle. And actually, the second section of this workshop is essentially dedicated to just to go over this. But this is really the action happens. But I'm going to save the spoiler for now. About the historical data, it can be useful. So this is kind of an interesting thing because this is an input and output at the same time. It depends really how you define it. But I mean, just to show how it is, if we go, for example, to data, RAMs, and by the way, on the repository, there are some files there, so you could explore. But the idea is that, I mean, we do have all those CSV files. They are compressed, so I mean, it doesn't take too much space. And let's open, for example, this one here, the retrieval. Oops, actually I compress instead of decompressing. So I decompressed here the retrieval. So this is the RAM that comes out from the graph. And it is the data as it is. So we have, for example, block number, depth available to set, global depth. I won't go into too much details of why specifically we are getting all of those, because I mean, in the end, they are going to be used for feeding the backtest and also the extrapolation. But the point is, I mean, this is one kind of input. And theoretically, let's say you could modify that file and use the use last file argument so that, I mean, you have a alternate history, let's say. And going back here, another very interesting file, and I think, let's say, if you want to really do a different simulation, I mean, you really want to tweak without coding too much, the best way of tweaking the simulation would be here on the governance events. So just to show how it is, it's again a CSV file. And the idea of this CSV file is that, let's say, we have the Ethereum epoch times here on the Ethereum block, and they represent the controller parameters after that block. So you can see that the KP has changed a couple of times. We also have the KI and the leak factor, which is 0 always because it has never enabled. But if it, for some reason, it's enabled, it's already built in. And there is also the period, which is about the period of the redemption rate. The idea is that the controller gets updated each hour. So this period controls essentially how aggressive is the controller update itself. It's like, so yeah. And a last thing is this enabled column here, which one means that the controller is enabled. If it's 0, the controller will not update itself. So the redemption rate is always going to be the same thing if enabled is equal 0 here. So for example, if you really want to do a different, and you guys are going to see that this is actually one of the challenges, is really what happens if you modify this file here, controller params? What happens if you, for example, make it, I don't know, maybe I was hacked and someone put, for example, for here. This is a very drastic change, actually. So, for example, what would happen if you put that? So, yeah, a challenge is exactly, let's say, do that and see what happens on the simulation, see if you can capture something. And of course, you must also take into account that the Ethereum block is there at time. So, I mean, you need to make sure that, let's say, the data that you are downloaded and the extrapolation time range fits on the Ethereum block. Okay. So going back here, and those other three here probably they are the parts of the inputs that are more complicated. So let's start, for example, with the state variables here, which are really the cadCAD state variables. So if you go, for example, to models and model and state variables, so yeah. You have so those are the state variables that are being used on the cadCAD model. I'm not going to do a deep dive in the cadCAD model because this is really the topic of the workshop 3. But let's say you have some inputs here that, let's say, unless it's overriding, actually out of those initial states they are set up during this cycle. So actually this is not the input that was out on the type on my side. But anyway, one thing that you could tweak is the params one here. So yeah, So those are all the cadCAD systems parameters. There are things here that, let's say, it's possible to tweak. So for example, one of them is this block time here. So the idea of this block time is how much seconds, each block is how much seconds. We are assuming that is 13 seconds. But you could also try, for example, to see what happens if it's, let's say, 15 seconds instead. Of course, it's not exactly that. The epoch time actually changes a bit. And you could have a mechanism that, let's say, uses stochastic values for the block time, but we didn't found out before that, let's say, the simulation is not especially sensitive to that. Let's say the variation is too small to justify increasing the model complexity. But you also have other things. So, for example, here is associated with backtesting, but you also have, for example, parameters associated with extrapolation. Like those two parameters, they really belong to the next workshop, because what happens is that we do have some behavioral models that uses things like this alpha here or the var lag. But I think that the exact explanation for them, maybe it's a bit too complex to put now. But you also have other things that are more easily approachable, like the extrapolation time delta. The idea here is that when we go to the extrapolation part of the digital twin execution, we can control, let's say, how granular we want our extrapolations. So we can have, for example, predictions for every 60 seconds or every hour, or for example, 3 or 4 hours. So it's a way of controlling the granularity.
Yeah, go on. Without going into the details, but can you say like what the behavioral model is modeling, like which behavior, like in general?
So the thing is that on this digital twin, we have two behavioral models. One is associated with those two parameters. Actually, it's associated, let's say, with those 3 parameters here. And another behavioral model is associated with this parameter here. The model that is associated with those 3 parameters here, it's a model that, let's say, it essentially takes the past actions that happened over the system, and it uses a, let's say, I'm trying to think here how I could explain what invoking a choose. What a word that nobody is going to understand. But essentially, it tries to, let's say, characterize what's the typical user action of the past based on, let's say, on the changes that you have. If we want to get into details here, we really talk about using an exponential weighted moving average together with a var model based on the state variables. But the point here is really, let's say, to try to characterize what's the typical user pattern over the past and simply do, let's say, a simple extrapolation to the future.
I see. So like the user behavior. So for example, like the 4th parameter, it says convergence swap intensity. So like I'm thinking that for that model, maybe you are trying to model like how intense is the people swap RAI with like so yeah, and maybe like for the other one is like a similar behavior, but it's not swapping, it's something else.
So as I said, we have really 2 models. We have this one, T1W, which is a bit more complicated to explain. This second one, the CSI, is actually relatively simple. The idea is that suppose that there is a difference between the market price and the redemption price. If there is a difference, you could also think that, let's say, there is an optimal swap that would make the 2 converge, that would modify bottom. So this convergence swap is really about having a stochastic factor that, and actually this parameter here is a percentage. So for example, if it is 100%, it means that you are going to sort a random number between 0 and 100%, and you are going to apply that optimal swap. It's a very simple model. And as we are going to see afterwards, especially on workshop 3, you can do, for example, sweeps for 10%, 30%. And actually, it's one of the outputs on the notebook. But I don't want to go too much deep into that because this is really the topic of workshop 3.
No, I was just like wondering on the high level behavior. So I guess one is on swapping, and what is EWM stand for?
So it's really about, let's say, capturing the user action pattern over the past.
And which action is it? Sorry.
What action? It can be anything. The idea is that the user, the users can do all kinds of actions, like, for example, swapping, add, remove liquidity, he can mentor, burn high debt, and I really don't want to enter too deep.
No. This was it. Yeah, this is clear. So it's like all the actions with like the liquidity of the token. Yeah, makes sense. Thanks.
Yeah, if you want a bit of a spoiler, the place where it is defined the EMW, let me remember where it is. It's not here. I think it's on the. I don't remember here where it was. Oh, I forgot here specifically where it was, but
but I think I get it. So essentially, EWM, you are trying to model like any type of behavior of like the user, like adding, removing, swapping, and then the swap convergence is a model that tells you like what is the swap that converges you like to the stable kind of like redemption rate. Yeah, I see.
Yeah, if you want a quick pointer, on the token state file of the parts, you have this P user action, which is really about where you put any behavioral model. And for example, the user model here is associated actually with a fit predict action here. And there is a step-by-step here that explains a little better, but anyway, it is really a topic of workshop 3. So
yeah, thanks.
So beyond this, another, the last thing that we have as input, general input, let's say, to the digital twin, besides the params and so on, is really the notebook templates. So just to show how it works, the idea is that if you go to the templates folder here at the RAI Digital Twin, the idea is that there are some Jupyter notebooks here. And we essentially use one. It's a very clever trick, but the idea is that if we go to that cell here, it's not very easy to show actually. But the thing is that this cell here on below load data has a tag. But I think that in order to see the tag, we would need to open on Jupyter Lab, happen to VS Code. But there is a tag here that, let's say, integrates with a library called JupTest that allows you to override the value here. So that, let's say, instead of using this base path, it would use the base path associated with a newer set of the newer data set. And the idea is that every time that I run the digital twin, once the execution is finished, it's going to run all of this notebook. So for example, any visualization that's defined here, it's going to be generated again on runtime. And let's say this is sort of a relatively quick way of, let's say, being able to have, let's say, reports that are being generated every time that you run. And for example, by using Plotly, it's also possible to have those interactive visualizations, which are super useful. And given those templates, I think that a natural place to start to, let's say, go over a bit of the output is really about the reports. So I did already, on the last workshop, I did already go over a bit some examples, but let's go here again. So let me open this one here. So this is the exact same template, but it was running, let's say, it was running at other moments. So for example, that template, if you see the dates, you are going to see that, for example, what it is. You are going to see that, for example, you have dates here like that has happened in May, while if we see here, probably it's going to be on June. Actually, it's not June, but it's a 4-day difference. But if you run, you are going to have different dates. And a lot of people already has executed that. So, they already sort of know like it is. But just to, go walk through some of the things that we have here. We have, for example, on the first one here, we have the Ethereum price on the past and also some extrapolations for it. we're going to go on workshop 3 about how we compute that. But the idea here is that we have a stochastic process. We fit the data that we have available, and we use that for generating several samples of price scenarios that we could use for, let's say, using as input on the other parts of the digital twin. And based on the H0 price, we could also have, let's say, compute the high market price based on the, yeah, this one is a bit more complicated, but yeah, we do have those scenarios. And one thing that I want to showcase here is that, for example, and I think this is it's one of the things that makes those interactive visualizations powerful, because I mean, you can see that there are several extrapolation scenarios here, and you can see that there is the CSI here and the OMW. This is sort of related to this discussion that we just have. So for example, on the purple line, I only have the EMM model activated in terms of, let's say, behavioral model. And for example, if I activate this one, which is the orange, we only have the CSI behavioral model activated. The EMM model is deactivated. And also we can have, for example, this green one, which is there is no behavioral model at all. All that matters is really the stochastic movement over the Ethereum price. And also we could have, let's say, this one here, the cyan line, which is really about making use of our behavioral model. So essentially, we are doing 4 different kinds of extrapolation here. There are different assumptions about what we think that's happening. So yeah, we have the Ethereum and the high market price here, but even more here is to actually inspect what's happening with the controller. So we have several metrics here, like for example, we have the redemption price, and we have on the past and the future, we have the redemption rate. This is percentage per hours, and this is percentage per year. It's important to always have in mind, let's say, what's the scale of the thing. So, I mean, because if you look at the percentage per hours, it's not very informative, but per year is more informative. There is also the proportional error, which is the error associated with the PID controller. The integral error here is 0 because we are not using the KI term. But if you guys change the KI term of the controller params.csv and put another number, you are going to see that this integral error is going to be activated. And also we have other things here, like for example, we have the notion of high debt or how much Ethereum collateral we have on the safe system. And also we control here, let's say, the high liquidity on swaps. So this is really about the Ethereum high liquidity. And it's kind of cool to see, let's say, what happens on each scenario. So for example, by the way, one thing that I didn't comment, you guys can see here on the past that we have the headline and the blue line. The blue line is really the real data. It's simply the data collected from the past. While the headline is what the cadCAD model think it should be. They are distinct because, I mean, you can always have some errors when, I mean, you operate on different time scales and so on. It's always difficult to have, let's say, a 100% representation of whatever you are modeling. So the importance of having those 2 lines is because it allows us to have an estimate of, let's say, of how close is the representation from the real thing. And I mean, one of the things that we have when we execute is really an estimate of error. Right now, the error is very small, but I mean, it doesn't seem to be small because, for example, the redemption price doesn't change too much actually. Let's say on the execution interval here, I think it has been amount. Let's say the final difference here was, let's say, 30014 against 30. So yeah, it's always important to have this scale here in mind. And yeah, and for example, you can see here that, for example, if I change, for example, whatever extrapolation scenario we are seeing, we can have very different predictions, for example, for what could be the redemption price over the future. Because, I mean, those extrapolation scenarios, they are affecting essentially what we are assuming how the users are going to react in the future. So, for example, on the scenario here that we use both behavioral models, the model believes that, let's say, it's going to sort of keep it the same thing in terms of the redemption price, and that the redemption rate probably is going to be around 1. It's not going to be, yeah, it's not going to be neither positive, neither negative. Or for example, yeah, the proportional error will simply bounce around. But if we see, for example, this one here, where let's say there is no behavioral model at all, we have all these variance here. So it has, yeah, you can have a range, but it's a bit more difficult to know where it's going to get at. And the important thing of having all those different behavioral models is because this is really, let's say, a way of, let's say, making explicit our assumptions. So it's always worth to, let's say, to be critical about, let's say, what we think is happening here. And for example, this purple one is just like the green, but this purple one takes into consideration the user past behavior. So it thinks that, let's say, it's a bit complicated here. On the green one, it tends to increase, but on the purple one, it tends to get steady, actually. I mean, you have high variance, but the redemption price tends to keep the same thing. While the orange one, for example, has a, yeah.
Like when you turn on all behavioral models, it seems the variance goes down, right? Like these paths like look closer together. Is it because essentially people are responding to the Ethereum variation in a way that like keeps the price stable?
So what happened? So we have this CSI model here that the CSI model is essentially one model that makes people swap so that the market price doesn't deviate too much from the redemption price.
I see.
So while the EMM model is essentially a data-driven model, but the EMM doesn't make too much assumptions about what could be. Let's say in a certain way, the EMM model is sort of like of the user action trend, while the CSI model is more of a fundamental model. This is that, let's say, you are assuming the user behavior. But anyway, I think that one of the points of, let's say, having this entire workflow of backtest extrapolation, having things, let's say, clearly segmented in files is really that, let's say, it makes it very easy, for example, to introduce a new behavioral model if we need to. We are going to do some walkthrough on next workshop about how we could introduce, for example, a third behavioral model. And yeah, we also have some stats here that actually the user action happens here. Because the 4 user actions that we do have on the current model is really about, let's say, swapping or exchanging liquidity on Uniswap, but also related, let's say, if, for example, the user is going to mint or burn high through the safe system. So yeah, for example, let's take just one simple model. So for example, this auto visualization makes much clear what's happening actually in terms of the behavioral model. The green one, it doesn't happen anything, just keep the same thing always. On the purple one, users are going to decrease their debt and collateral slowly over time, and also decrease their liquidity in Uniswap. The orange one is, well, it's a bit more fuzzy, but one thing about the orange one is that all action happens only on Uniswap. On the orange one, the users don't mess with the safe system. While, for example, the green one is really a mix of everyone. So, for example, when we introduce behavioral models, we are really talking about, let's say, how we can affect any of those. We're going to play that on next workshop. So yeah, and that was about the report. I hope that, yeah, that was about the report. Just to finish the input and output part, I just want to show a bit how the data looks like. I already showed the data that was retrieved, but I also want to show the backtest and extrapolation ones. So let me open the thing. So yeah, I guess that I had a problem here. For some reason, I'm not being able to extract them. Let me see if I can open directly. Okay, so I guess that I will need to practice my speed hacker skills here. So let's go.
We need a soundtrack or something.
Yeah, I mean, I'm going to practice here my speed hacker skills, and okay, we'll go over it. No worries.
You can sing a little bit also.
All right, go for it, Patty. Gyame, if you're in the call, if you can hear us, there were a few questions in the chat about RAI. Maybe we could cover those while Danilo's hacking.
Yeah. So, okay. About the chat, so David Krepp has asked about the KP and KA params. It's associated with the PID controller. The idea is that
Danilo, if you want to keep hacking, Gyame might be able to cover the RAI questions. Or are you already done?
Yeah, I already done.
Oh, okay.
Maybe we could go over the question. But okay, I did speed hack here, and okay, I did open, for example, the extrapolate CSV file. And I mean, essentially what we have inside this file is each home is essentially a cadCAD time step. And on each time step, we have things like, for example, let me see, we have things like, for example, the tier on price or the market price on each time step, the spot price, and also things like the high reserve, the tier on reserve, high depth, the tier on locked. So, for example, if I pass here, for example, high depth on plot. Strange. Maybe the market price. Yeah, you would have. I think I know. It's weird because I didn't post-process the data, so there are some tricks about that. But anyway, probably the report notebook is a better reference because the report notebook I did already post-process the data. It's because this data set extrapolation contains not only the variables, but it contains also the Monte Carlo runs, the substeps. I mean, you have all the scenarios that you see on the report is contained there. So it's sort of mixed and it's not just test plot. So be aware of that. But yeah, just to show, let's say, what contains here. Everything that you see on the report is contained on this extrapolation data set. And if we look, for example, the backtesting one, it's the same thing, actually. But the backtesting is on the past and the extrapolation is on the future. So both are cadCAD simulations. It just changes, I mean, if it's past or future. And yeah, that's it, let's say, for the outputs. I mean, you guys already know what the report looks like, how the data looks like, and also where you could, let's say, intervene to change the input. If you guys want, we can have a quick question, because if not, I'm going to move the execution cycle to really, let's say, see the code and see how this input is consumed and how this output is generated. So yeah, we have time for one question.
Yeah, if Henrik or Davide or Joe's, I believe you three were posted questions. If any of you want to get yours clarified, feel free to speak up.
Can go start. Yeah, Henrik here. So I was looking at the script you have in the model parts, the time script. Can you explain how you? It's sort of like fascinating that you can convert height into time. How does that actually work?
How I convert the time. So when you mean time, do you mean? Let me see here.
It's the time script in the Digital Twin version 1 model parts.
You mean the
Translating blocks into time. Is that what it is?
Well, that's what I'm guessing, because you also you define the time delta in hours and seconds past, and you basically use block height and time steps. And I'm sort of like, how does that resonate? I don't understand.
Yeah, so this is a bit tricky, because what happens is that let's say when we collect the data from the genome mainnet, well, what happens is that the time on zero block net is not, it's not that you have seconds or whatever, you have actually block heights. So you don't have a one-by-one correspondence with real time. But until it's also the difficulty that, let's say, when you do extrapolation, yeah, so the issue is that, let's say, when we get the hand data, so let's go here to the retrieval here. When we get the hand data, we don't have time, we have block heights. This block height should be converted to a timestamp. And what happens is that the time difference between those timestamps, they are not the same thing. Sometimes they are 40 minutes, sometimes they are 45 minutes, sometimes are 1 hour and a half. So we have this issue generally when you analyze blockchain data that time is never on uniform intervals. So the reason of why the code is that way is, I mean, exactly because of that. Because I mean, what we need to do here is the following. So the idea here is that, for example, when we get the data as provided in heights, we need to get the delta in heights. And we need to multiply that by the block time. The block time is in seconds. So delta here is being actually, yeah, units of delta multiplied by block time in seconds. So we have seconds here. And it's one thing that's always used for doing any kind of simulation, which is to define, let's say, a general unit of time. So for example, in this simulation, we are always going to use seconds. And the reason of why, for example, we have this if clause here of why if heights is known, then you have this, if not, you have that, is because these heights here, we only use on backtesting, and backtesting uses historical data. So if we are backtesting, if you are providing historical data, we need to compute these delta heights. If not, you can see that, so for example, if heights is known, we are on the extrapolation mode. On the extrapolation mode, we do, the time delta that we pass in seconds is actually the extrapolation time delta, one of the parameters. So for example, on the way that's configured here, this time delta is always going to be 1 hour if heights is known. And if heights is provided, it's something that, let's say, we are getting from the real data. So yeah, it can be 45 minutes, 50 minutes, 1 hour and 20 minutes.
So when you forecast, it's actually a huge uncertainty depending on the activity, because
you started to use,
you're forecasting in time, and all depending on whether in a bull market or a bear market or whatever you are, then the activity on the chain can actually sort of, it's just a wild guesstimate in terms of what is actually forecasting 2 weeks. Is that correctly understood? Because you actually depends a bit on the activity. It's not cast in stone.
So it's not exactly, because I mean, what I was discussing here is really about the question of time tracking. The function of this file time.py is really to make sense of the time when you are handling data that comes from blockchain, because you don't have, as I said, each block height has a different timestamp.
Okay, so you resolve backwards, and then you basically going forward, you just say, well, a second is a second.
Yeah, let's say this is just resolving time. It's just to make sure that the timing is consistent.
Okay.
The issue of uncertainty about forecasting really depends on several factors. I mean, depends on the behavioral model that you use, depends on how, for example, how this model compares to the past, and also this behavioral model is built on top of the of how we are describing the high controller, so it must be accurate. Yeah, I think that the question for certainty is, I mean, it's a complex topic in its own.
No, I think I at least enough to I can understand, so enough to read it. So thank you.
Cool. Thanks, Henrik. All right. Yeah, we can keep chugging forward.
Yeah. So for the next section here of the workshop, it's really now about the execution cycle, which is really, let's say, what makes how we do consume those inputs and how we transform those outputs that I just showed you. So I did show this diagram before on the first workshop. And the idea is that we do have a code base on RAI called executionlogic.py. And essentially it wraps everything of this together. I'm going to show here the next slides because this is really the mapping of, let's say, of what I thought that were the components. This is really the map of those components towards files. So yeah, we have the execution logic here as wrapper. The thing that, let's say, makes you able to, let's say, pass, for example, python-m RAI Digital Twin. And by passing that, it's going to do everything. Those components are really encapsulated in several pieces. So for example, we do have the cadCAD model here, which is encapsulated on the models Digital Twin V1 folder. And also we have the types here, which also contains, let's say, all objects that, encapsulate, let's say, what's the token state of RAI, what's the controller state, what's the controller params. It's really, let's say, about having classes as definitions of all the primitives that we want to keep track. And for the other components like data retrieval and preparation, we have separate files here, like retrieve data and prepare data. So retrieve data is about scraping data from the graph, and prepare data is really about taking this ham data and convert it, and let's say making use of the types so that we have things that are readily consumable by the system representation. We have here another file for the backtesting, which is, for example, we do have an error metric that is printed when you execute the digital twin. And the way that you define the loss function, how it is computed, it's all here on backtesting. We can go over it. The system identification component is also encapsulated in those two files here. There is the stochastic.py, which is really related to any stochastic process, like, for example, how we, for example, create a handle distribution for the Ethereum versus USD price, which is a critical measure. So how you fit and how you generate this contained here. And here on the system identification, it contains some code for example, the EMW model, which essentially try to characterize the typical user action on the past. And the last part about extrapolation, the two places where extrapolation happens is on the stochastic and on the cadCAD model itself. So to go over how things are wrapped, I always find that, let's say, going over the execution cycle is a good start point. The idea is that if you go to this file here, execution logic, you are going to have several functions, but the critical one is really this one here, extrapolation cycle. And you have several parameters, like, for example, most of the CLI parameters, they just map into that, like how much days you are pulling, how much historical lag you want to have, how much price samples you want to have. So we are doing 10, but you could do, for example, 50 or 100 if you want to have more data points. And how much extrapolation samples, you could put that as 3 or 5 to also increase the number of points. Or, for example, how much time steps extrapolation we want, and so on. So I sort of tried to separate here where things happen. So for example, the first thing that we do here, where I select, is really to retrieve the data. So there is a lot of boilerplate logic here really to make sense if you want to get the last data or not. But the main point here is really that at some point we need to get, let me look here. Yeah, the main point is that, let's say, if we use last data is false, so that we do not want to retrieve what we have stored right now, we must call this function here called retrieve data that's going essentially to download the data. This download data is defined actually on here on retrieve data. So if we go here, you are going to see a lot of code essentially for retrieving all the statistics from the graph, getting the system states from the graph, retrieving the safe history. It's really a long topic. We could almost do a workshop about how the graph works and so on. But the main point is, in the end, we really want to go to the graph and collect everything that's useful for us, and in a way that makes sense for the time interval and so on. And okay, going back here. So yeah, this is just for collecting this file here, the retrieval.csv. After we have this retrieval.csv, going back here to the extrapolation cycle, we get here before preparing data. So as I said, preparing data is really about, let's say, picking up that home data and transforming into things that are, let's say, more easy to consume on the simulation. So to the start, we have this load backtesting data. We have also this function here for loading governance events. It's really boilerplate code that, let's say, it's the SSV, assign some things, create the token states, create the PID states. Just to be clear, what is token states and PID states? It's because, I mean, on the high simulation, we do make use of several types. So for example, we have several measurement units here, just to make sure that, I mean, it's not ambiguous what everything means. But a great deal of the actual dimensions is really about, for example, changing the controller state. So we are interested in changing the redemption price, redemption rate, proportional error, integral error. Or for example, the token state, which is really about, for example, how much height there is in liquidity, how much high depth there is, and how much material collateral there is. And yeah, it's really a lot of things. It's a large model, but yeah, but the main point is that after we prepare the data here, essentially we have created instantiated autos class that we can feed inside the cadCAD model. So essentially we encapsulate everything through backtesting data and governance events. After that, we are ready to run the cadCAD model, and that's what we do, for example, here with backtest model. So if we go here, we have another file. So for example, I need to prepare here the initial state of the cadCAD simulation and also prepare the parameters. So I set up, for example, the controller state. So for example, I get the redemption price at the beginning, the redemption rate at the beginning. I assume that the initial error of the controller is 0. This is an assumption, but there is no way of retrieving that error. So, I mean, we need to go with that. This is the origin of the error. This is one of the reasons of why the backtesting line is different from the historical line, because, I mean, we do not know what's the actual error. We do not have access to that data. And yeah, we also need to set, for example, the parameters here. I mean, it's really a lot of boilerplate code. And after we have all those parameters here on the easy run, we can, let's say, execute the cadCAD model by using the historical data as using the historical state and seeing what the cadCAD would think it should be. And yeah, I won't go, I mean, it's a lot of steps there, but after the backtesting here, we have some things like, for example, we can know, for example, the absolute error that the cadCAD model does against the historical data. This is printed on the terminal on, let me see here. I think it's, here, simulation loss. So yeah, we run the cadCAD model and the idea is that, let's say, we have this CDF, which is the cadCAD model. We have the test DF, which is really the historical data. And we can compute the loss. We compare the cadCAD result against the historical data. And yeah, and this simulation loss, how is defined? What are the metrics? It's all defined here at the backtesting. So yeah, it's another long topic here. I mean, if you guys want a challenge, I would say that one possible challenge would be exactly, let's say, what are the validation metrics that is being used in backtesting and how they are computed. Okay. And after we have that loss, we can go over things like, for example, fitting the stochastic process and extrapolating some of the signals. So you can see that it's all coherent with the diagram that we have right here. We extrapolate past that, we compute validation metrics, we fit stochastic process, and then we extrapolate feature signals. And these extrapolate signals here, it's going to fall here on the generated channel samples, because this is really about, let's say, generating values for the USD price over the future. The way that it works is, let me remember here. Actually, I think that I went into wrong one. So let's go to the stochastic feed. And the way that this works is really, we have a Bayesian model here about how Ichiro should behave on the future. We fit that model. And by having that, we have some parameter estimates about, let's say, Andrew Clark is the best expert for that, so I won't go into details. But the idea is that we find those two parameters for a random distribution, and we can use that for sampling as much time series we want about the Ethereum price. And yeah, we got those parameters, get back, and after that, here with the stochastic params, we can provide that for example, to extrapolate signals. So to extrapolate signals, take those parameters, take the amount of data that we want to generate, take also the initial Ethereum price that we have, and how much samples we would like to have. And yeah, it's just about generating Ethereum USD prices time series. After we have those price signals, what we can do then is to really extrapolate, let's say, data for the token states and the controller states based on those price scenarios, and also based on the, let's say, on the starting point that we set through the historical data. This is done by through here the extrapolate data. This extrapolate data essentially makes use of the cadCAD model again, but in a different manner compared to the backtesting. Here we are using the behavioral models. On the backtest, we do not use the behavioral models. So we need to set up the parameters for the behavioral models here. It's really a lot of things. Like for example, here I do a parameter sweep over the UseML model. It can have false or true. So I'm going to get scenarios with both using or not use the model. At the same time, I can, for example, sweep the convergence swapping test here between none and 25%. Suppose that one of you guys want to know what happens if it's 100% or 50%. You guys could simply modify here. So we would have a lot more scenarios if we do that. And probably this is going to be a challenge of the next workshop. And yeah, so this, for example, it's all, for example, setting up the parameters so that it's coherent with what we want to extrapolate. Here we set the initial state. And by having the params and also the initial state, we can run the simulation here in a way that, let's say, you can extrapolate and we post-process until we have the CDF, which is really the data frame here for the extrapolation. And yeah, after we have extrapolated that data, we can export the results. So for example, here on this step here, it's really about this library called paper mill that allows you to execute a notebook and export it to something. So for example, here we provide the input path and also where we are going to export. And I have parameterized that notebook template so that it consumes from the extrapolation here. So I do an analysis notebook that simply goes on the extrapolation, do all visualizations that I want, and it exports to HTML file. And after this is done, we have done everything. So you can see that on several steps here. For example, I have, for example, two CSV. So for example, extrapolation DF to a CSV. It's through this way here that, for example, generate extrapolation CSV file. Or I have, for example, let me see here, backtest results to CSV. So I generate the backtesting file here. Or the historical file, for example, I generate here. And yeah, that's how the input and output is generated overall. And that's a summary of the execution cycle. It has been, there is as you can see, there is a lot of things to really dive deep. I didn't enter the cadCAD model yet. This is going to be topic of the workshop 3. So we are going to see how the cadCAD model works, how we mutate the controller state or the token state, and also how the behavioral models are implemented, how we can tweak them, how we can adapt the behavioral model. So yeah, to questions and answers, I would like to put here the challenges that I find interesting for this workshop. First one is about, for example, plotting the data that we have, but on a separate notebook. So we have all those CSV files here on the HUMS folder, and the challenge is the following. Are you able to do a notebook that consumes from that and, let's say, plot meaningful results? So one option, for example, would be to plot the historical data, or you could plot the extrapolation data. It could be whatever you would find interesting. Another challenge that we have is what happens if you change the controller params file and run the simulation. So for example, if the KI or the leak factor is not 0, what is going to happen? Or if you change the KP, what's going to happen? So yeah, the challenge is really to modify that. And I mean, tell us next week what you did notice. The third challenge is about the notebook template. So if you go, for example, here to this template here, the extrapolation, let's say this is the template being used for generating those HTML reports. Can you modify it? I mean, for example, if you modify the new visualization, or maybe take a summary statistic, like for example, take the average of the differential price. Can you make that modification, run the digital twin, and make sure that it's working? So the challenge here is really to modify this template and run the digital twin. And the last one, probably it's a more complicated challenge, but the challenge here is, are you able to create a new notebook template? And creating a new notebook template is really about, let's say, perhaps duplicating that extrapolation template here and going to the extrapolations file here. So we have this logic here for generating a report based on that template. And probably you would need to copy and paste that code here and modify so that it uses your new template, the existing one, so that it generates 2 reports instead of just 1 report. So this is another challenge. And yeah, that's it. I mean, we did run a bit over time, but yeah, time for questions and answers. And yeah. So first question here about NDK accuracy. So he's asking about how accurate is the forecasting capability currently. To be fair, I'm not exactly sure, because I did develop the framework, but let's say once it had been handed over, I didn't operate. So I'm not exactly very aware about the current performance of the behavioral models. But one thing is for sure, if you want to have any kind of forecasting capacity, what happens most of the time is that, most of the time is you develop a model, you validate it, and for a period of time, it works just fine. But if you do not properly maintain it, what happens is that the user behavior tends to change with time. And also, sometimes you have, let's say, hyperparameters or parameters that need to be turned again. So what I mean is that, let's say, the accuracy of forecasting really depends on the continuous operation. So I'm not exactly aware what's the current accuracy, because I'm not operating. So, it was very accurate when I did do the handoff, but I'm not exactly aware, let's say, how accurate it is right now.
That's convenient.
No, but that's actually part of the problem, isn't it? That if it's like handing over a very expensive surgery tool to somebody who may or may not be able to use it.
But I think someone in Reflexer Labs should be operating it right now, right?
Maybe. What I mean is that, let's say, I'm not exactly very aware, let's say, how it's being used right now on a continuous, let's say, operation.
Yeah, Guillaume might have some insight on that.
Yeah, so like we have someone that worked closely with BlockScience and that used the model a lot. I personally didn't use it, but yeah, maybe I could ask him to join for the last session. Maybe he could have some good insight for you guys on like how it turned out to work in real life.
Yeah, that would be awesome.
One would imagine it's used for a business purpose, so that could actually be interesting. Or maybe BlockScience needs to set themselves up with the monthly update service.
Like the original goal was to decide on the controller parameters, right?
Mm-hmm.
Like it turned out that it's very hard to set good parameters, but like through this research, we really understood a lot of like things, intricacies, and detail that we wouldn't have thought of. So like the research process was still very useful for us to understand how, the dynamics of all these things.
But do you then have a sort of a risk governance forum similar to Maker, which is, I guess, pretty advanced quantitatively, doing all sorts of dimensional simulation, I guess, 24/7?
You mean on a real-time basis?
Yeah, I mean, the way I saw Maker forums, risk governance, well, it's actually they have regular risk reports that been, of course, as you already mentioned in the beginning last week, there's a huge collateral exposure to USDC, and the question is, what about it? And what if you want to be a stable coin? You also need to basically reverse stress test yourself and figure out, okay, how to get out of it. And I guess that's why they're so eager to get additional collateral, including real world assets, into their protocol to reduce dependency on crypto, because all their risk simulations found that they're heavily influenced by what happens in the crypto market. So you could say it's not really stable outside crypto, and they want it stable. I guess that was at least the reflection over the summer, but I was just thinking this sort of modeling that you have here would be something that you should probably use from a governance perspective regularly and report on, so that the community will be able to understand what are the risks associated with the protocol, and you may maintain proper reserves to go through stress periods, not just forecasting point in time, but actually managing through the cycle.
No, yeah, totally. I mean, like the research is open source, and I believe like we will be adding, I mean, following up research and new data over time. But yeah, like the original goal and like in the core thesis of Reflexer is governance minimization. Mm-hmm. So the whole original idea behind having a controller was to remove this like monthly or weekly debate that Maker had to decide the stability fee, where they were talking on the forum, oh, let's move it up like 1%, move it down 3% to incentivize more lending and so on.
Yeah.
To have it replaced by a controller that you set the parameter once and then there wouldn't be a need for governance. So obviously in practice there will be always a small thing that you tune in, but like is the direction that we are like where we want to get.
Thank you.
Yeah,
really
I'm just
Go ahead,
curious. I'm just curious. Like since you started operating the controller, has it been quite stable? Like, have you had to make changes, like maybe at the beginning to adjust, because it's always hard to predict. I mean, notwithstanding the great research, maybe as soon as you start operating, you tune a bit, and then it's been quite stable, or you've had to make changes over time?
No, yeah, we had to make changes at the beginning. Like looking back, we were a bit naive, because like we originally started completely ignoring like the liquidity mining incentive. We had done all this modeling with BlockScience, and we left out the liquidity mining incentives. Yeah, speculation, and people first, like there was two problems at the beginning. Like people didn't know that it was supposed to be a stable coin and wanted to speculate on the price of RAI, thinking that the token will go up. So that was quite funny. And there was then another phenomenon that like our incentive models were like people will buy the token to do this, to participate into these different incentive schemes that will prop up the price and skew everything basically.
Yeah.
So we had to modify the incentive schemes to avoid the token going to the going to the moon and the controller getting crazy. But yeah, we also had to like lower the KP constant, so like lower the controller strength. Yeah, we originally picked a quite conservative parameter because we wouldn't know how we would go once we launched, but when we launched, we realized that was still very strong, and so we lowered it. And yeah, recently we brought it up again, and yeah, right now we have reached like more or less stable mode, I believe.
Yeah, and thanks. This is great. And just a curiosity, like you're bringing it up again. Is it related to like some evolution, some shock in the crypto market or something? Like
we are bringing it back up because I mean, we did that like 1 or 2 months ago, because after the original launch, we lowered it so strong that it was almost like if there was no controller.
I see.
So we brought it back to life.
I see. And one last comment on this. I think this research that also Danilo, like this tool that Danilo presented, could be used for testing like scenarios that are far from average, right? So like if you introduce like a 10 sigma shock, like related to what Hendrik was saying, like stress testing the system, right? I'm not sure if you've used that, but in my mind, that could be like a very useful thing.
Yeah, it's true, but like the model always work under the assumption of the model, obviously. And like, if you try to model extreme scenarios, like you likely some of the assumption of the model wouldn't hold.
Will break.
Would break, or like like a typical one is that turn out that the market is not efficient at all, and that people are not taking advantage of arbitrage opportunity because it goes too fast or because they are not aware, this kind of thing. So
makes sense.
But it's still interesting to look at the model and like see how it would behave under those assumptions, even though in real life it wouldn't. It gives a feeling of like where you should look at.
Sorry.
No, I would only comment that, for example, the way that we have separated, for example, the controller logic from the behavioral logic is exactly also to allow to explore, for example, what would happen on their different assumptions. So, for example, one possible behavioral model, submodel, let's say, that we could use is something like, for example, suppose that 10 days from now, people remove all their liquidity from Uniswap. Or, for example, suppose that, let's say, someone did a large swap, or someone, for example, did burn out the debt. And the way that is, let's say, created the digital twin allows, for example, you could turn on and off several behavioral models at once. So, for example, you could have, let's say, this weird interaction happening, while you also have something happening, like, for example, people making arbitrage trades, or people simply replicating, let's say, the past pattern. So, the exact scope of, let's say, of how much we predict and so on also depends a lot on, for example, what we want to ask to the model. We do have the controller implementation of the model, but we also need to, let's say, know, let's say, what are the behaviors that we want to, let's say, to predict against.
Yep, makes sense.
Yep.
Awesome. Really interesting discussion. Great questions, everyone. I think that we'll wrap up the session then, since we've gone a bit over, but always good to have everyone. Danilo, any last comments from you on the challenges or anything else? We finished all the slides.
Yeah, that's it.
Cool.
30 slides there. I'm going to do a push on the GitHub content list of challenges. And by the way, feel free also to, if there is something that, if there is a question or a challenge that you would like also to do other than the ones that I proposed, so feel free to do it. And yeah, next week we are going to do a more deep dive on the actual model code, into the actual cadCAD model, and also the behavioral models, and how to add a new one.
Yeah,
maybe introduce some chocks.
Really cool. Yeah, great opportunity to explore the model. I mean, pretty much free reign to create a challenge for yourself, and then if you submit it to GitHub, you will get the PO app, as we mentioned in the first session. So there's something at stake. Cool. Yeah, we'll follow up in the Discord then with the links from today, the slides, and the recording. Otherwise, we'll catch everyone next week at the same time. And we actually have an hour and a half scheduled next week. So we were planning on a longer session, and hopefully we don't run over that. But yeah, we'll see everyone next week. Thanks for joining.
Thank you, guys.
Bye, guys.
Bye. Thanks, Sunil. Thanks, Kwame.
Bye.